Okay, so we're going to talk about type of memory. We've talked about main memory in this class. Now we're going to talk about cache memory, which is just a smaller subset of your main memory. And we'll also go over a piece of hardware that could be used for very quick lookups, and then different policies on how to use cache memory. So just a very, very quick review on how memory works. If you remember, if we wanted to read from memory, this was our slide where we said we had 4 nibbles. 4 bits, A, B, C, D, 4 bits here, 4 bits here, 4 bits here. And we wanted to pick one of our memory locations and copy its content to a register. So what we would do is we would put on our decoder the address, the binary address of which nibble we wanted to copy its contents. So if we put 00 here, that would be the input to this decoder, which would turn this line on. This line being turned on would turn on all of these AND gates, and the 4 bits A, B, C, and D would get written, would go into these OR gates, and A, B, C, and D would show up here. Because these 3 lines are off, the decoder shut those lines off, all of these bits would be shut off by all these AND gates. So it sends all zeros into these OR gates, and that way only 1, 2, A, B, C, and D come in. Okay, so, and if you remember writing to memory, if you had data in a buffer, if we had bits W, X, Y, and Z, and we wanted to write them into one of these 4 nibbles, we would put on the address, the MAR, the memory address register. We would pick one of the 4 nibbles we want to write to. Let's say we pick 0, 1. That would turn this wire on and these 3 wires off. This wire being turned on, going into all of these, would allow these 4 memory cells, these 1-bit memory cells, to take on a new value. So W would get written into this box, and X would get written into this box. Y would get written into this box. Z would get written, the contents of Z, where is it? Z goes along here, would get written into that box. The other 3 nibbles would be left alone because we didn't turn their wires on, so they would remember their old values. Okay, so that's just basically a little review on how memory works. So when you're accessing memory, whether you're reading or writing, you put the address that you're reading and writing to, you put that in the memory location, and then it goes through a series of ANDs and OR gates to decide if you're going to be reading or writing. So obviously, the larger the memory is, the slower it will take. So for example, if instead of trying to write 4 bits to 4 nibbles, if we wanted to write 32 bits to, let's say, 32 gig of memory, that would require all the electronics to be, that you see in this picture, to be multiplied by 32 billion. So the bigger you make your memory of all the locations you're trying to write to, the more choices you have, the longer time you have to take before the 4 bits get written into the locations they want to get written into, or being read from. So, I'm sorry? So, okay. So anyway, and obviously if we had 32 gig of memory, instead of these OR gates having 4 inputs, they'd have 32 billion inputs. So the bigger the memory is, the good news is you can stuff more memory into it. The bad news is it takes longer to read and write from it. So if you were designing a processor, you might say, well, why don't we have a lot of main memory? The good news is you can fit more programs into it. The bad news is when you run and execute an instruction, right, what were the stages we talked about? You fetch the instruction, you execute the instruction, you read the input, you perform some math, and then you write the output out to memory. Well, if you make your main memory really, really big, you're going to have to slow those 2 steps down. It's going to take longer. So then you start thinking, maybe we should make the memory smaller so it'll run faster. If you make the memory smaller, then you're going to have to keep going out to the disk drive because you don't have all your program in memory. So along comes the idea, why don't we have a really big piece of memory that's slow, and a really small piece of memory that's fast. Hopefully what we're looking for is in the smaller piece of memory, but if it's not, we'll go to the bigger one, and then just take longer. So now instead of your read and write cycles being, one step, maybe we could have one step check the small memory, which we'll call the cache memory. If it's not there, then have two more cycles to do the larger one. And the idea is to put important stuff here, but somewhat important stuff here too. And maybe we can even do layers of caching, a small and a medium cache and so on. So now we have kind of a hierarchy. So with cache memory in front of main memory, when a processor is running and it goes to access some storage, the storage will of course be out on the disk because the disk drive has everything. It might be in main memory, and the main memory is going to be a subset of the disk, and it might be in the cache, and the cache would be a proper subset of main memory. So anything that's in the cache is always in main memory too. So if you go out to the cache and it's there, that's great. You could access it very quickly, and the access time will be short. If not, then the next step is to go to main memory and get a copy of it. So if we had a CPU, I'll talk about the TLB in a second. And we go to read from main memory, and maybe it's there, maybe it's not. If not, we could go to here to read or write from it. If it's not there, we go out to the disk drive again. Now this is a very, very small cache called the translation look-aside buffer. We talked about this once before, but it's a piece of hardware like this. This actually doesn't run in software, like searching through software looking for a match. It's a piece of hardware where basically, if we're looking for 2 bits, these 2 bits represent 0, 0. If we're looking for the page 0, 0, we can do a hardware comparison to this page, which is also 0, 0, which is a direct match. And if this is a direct match, this wire turns on. This 0, 0 and this 1, 0 do not match, so this wire is turned off. So the contents of this piece of memory actually get copied into the location we're going to. So we can put a page number into a buffer. We could put a page number into a buffer, and if it directly, we can simultaneously compare it to anything. This would be obviously along the list. Simultaneously compare it to all. If we ever get a match, the wire turns on, and the wire will then take the page's content and copy it to where we're going. So that's a piece of hardware, the TLB, very small cache. And we can take the memory location we're looking for and simultaneously compare it to all and instantly find out if it's there or not. So the other thing we could do is we could have the CPU connected to the TLB and the cache at the same time. In other words, just check it here. And if we find it here, we could just call off this search. So it's an optional thing to put this small piece of hardware in front of the cache. So in this case, we're just kind of considering everything. So, okay. So suppose you're looking for a variable. Your program wants to read a variable X. And the variable X is written out on the disk drive, and it's also in main memory. But it doesn't appear in the cache, and it doesn't appear in the TLB, the translation look-aside buffer. So if you want to read its value, you can check, is it here? Simultaneously, you can check if it's in the cache. And you find it's not there. So now what do? You have to go to the next step. You look in main memory. Oh, I found it here. So now this is kind of, it's not working out in our favor to have a cache, because if we didn't have a cache, we would have looked straight in main memory and found it. Now we're looking here, realizing it's not there, and then looking here. So the fact that we had the cache slowed us down here. It would have helped us a lot if it was here, but once in a while it won't be. So now we read this. We're reading from main memory. And the segment, the piece of memory we're looking for, is not in the TLB, and it's not in the cache memory. So now the question is, if you're reading this, should you read the value and have your program keep running, or should you take a timeout and put a copy in the cache, and maybe even put a copy in the TLB, because you think, well, if I'm reading it now, I might be reading it again in the near future. So it might be worth it to take the time to propagate it up, or not. What would make you decide whether you want to do that or not do it, or what's the pros and cons? Well, the con is the time it takes. If you want to put this variable in the cache, you're going to have to find something here to kick out to make room for it. So you have to kind of keep track of what's sitting in here and not being used recently, and maybe kick that out. And that's going to take some time. The advantage would be if you're using this in your code now, you might be using it again in the very near future, and we don't want to go searching all the way again. So we could move the value up close. That's a kind of an operating system / computer architecture decision. So what we could do, if we're going to go read it, we could also find something here to kick out and put this copy in here. And then maybe even put it into this piece of hardware. So now if we need to read it again, it'll be right there. We'll read it very quickly. That's possible. Now what if you were to change this value? What if you changed x to 3? Right? So that means we're writing. We're writing to our memory hierarchy. Now if we find the copy we have is right here, we can make the update very quickly and we're done. In fact, that's the whole point of having layers of memory. If it's a variable with writing and reading and writing from often, it's nice to have it very close to the CPU so we can write it quick. Now, would you, if you were changing x to, let's say, the value 3, would you write the 3 here, and here, and here, and here, or not? And what would be the pros and cons of doing that? Yeah?
I would only write it in one spot to save time.
To save time, right? So we're changing x to a 3. If we put it here, and we're done, next time we want to read it, we're going to read right here. We don't need to read these. We're just going to read it right here. The one downside would be, suppose you changed it to 3, and you put the number here. Right? We changed it to 3, and here it's a 2, and here's a 2, and here's a 2. Could this hurt us? Well, first of all, suppose we didn't use this variable for a while, and we need to kick it out to make room for something new. We don't want to just erase it. We want to say, this is different from this, so we want to change this to a 3 before we kick it out. Otherwise, we'll lose the fact that we made it 3. The other thing is, suppose some other program is reading from here, right? And let's say you had multiple processors and they're all sharing the same main memory. Then you might want to, every time you change it, write it back. But that becomes, now we're almost like, why are we doing this? Because every time we write it here, if we have to write it everywhere, then let's just get rid of this. It's taking up too much time. We have to write it everywhere. So it depends, is the variable shared by other programs is going to determine how much updating you need to do. So we could, so for example, suppose a decision was made, this variable is sitting around, hasn't been used in a while, we decide we're going to take it out of the TLB and we're going to take it out of the cache. Well, we have to take this value, copy it to here, and then we can wipe these out and make room for something else, which would look something like this. So now we've propagated the new value back to here, and the fact that it's on the disk drive is 2 doesn't matter. As long as nobody goes to the disk drive looking for it, we'll be okay. So, so this is what it could look like to us. Okay. And the reason we would do this is this variable is not popular anymore, so we need to make room for other variables. Okay. Okay. So, okay. So we kind of have a debate, you know, two different types of policies. Do we want to write the value back, or do we want to write through? So write back is a policy where, like this, if we change x to 3, we can leave these stale copies of it around, because the only time we'll ever reference it, read or write it, is from the CPU, and it will always hit the one closest to the CPU and read it from here or change this one. We just have to be mindful, if we ever remove these, we have to copy it back at some point. We could also have the policy that every time we make a change to a variable, we write it to every location going all the way back. This is now not saving us time. Obviously, this is now making writes take longer, because every time you write a variable, you have to write it everywhere. So the only advantage to using a cache, if you're using the write through policy, would be to make reads go faster, but all your writes are going to be slower. So we have to write the cache write back policy and the cache write through policy. So So when a change is made, you only write it to you update the piece of memory that is closest to the CPU. You don't make the updates all the way back to the hard drive. The write-through policy is the cache policy, where if a change is made to a page or a piece of storage, the corresponding main memory is updated, and obviously those writes go all the way back through the disk drive. Okay. So here's just some examples of whether or not there's an advantage to using a cache. And sometimes there's an advantage and sometimes it's not. And a lot of times, the laptops you have a cache on it. They'll turn the cache on, and if they find it's slowing things down, they'll shut it off, and you'll just operate right out of main memory. So let's say the probability of a reference, you go to reference a variable in a cache, we'll call that, the probability of it being there, we'll call that the hit ratio. And the probability that it's not there is the miss ratio. So for example, consider if you access a cache takes 1 nanosecond to access, and main memory takes 10 nanoseconds, what value of P, the probability that what you're looking for is in the cache, would make it, and it would be advantageous to use the cache. All right, so let's see, without the cache, anything you go looking for in memory is going to take 10 nanoseconds. If you don't have a cache and use main memory only, anything that's in main memory will take you 10 nanoseconds to read it. But if you use the cache, then some of the time what you're looking for is in the cache, and you'll read it in 1 nanosecond, right, because it was in the cache. And sometimes it won't be there, which means it'll take you 11 nanoseconds. 1 to look in the cache and find it's not there, and then 10 more to find it in main memory. So what would be a hit ratio that would make it worth using the cache? So you would take the hit ratio, whatever percentage of the time what you're looking for is in the cache, times how much time it takes to look in the cache, plus the miss ratio, that's the percentage of time you're going to look in the cache, it won't be there, now you have to look in main memory. And then how much time does that take? The cache access time plus the main memory access time. So now we have the hit ratio times 1 plus the miss ratio times 11. Right? When you end up doing the math, work out the math, the hit ratio, as long as it's greater than 1/10, it would be advantageous to use the cache. So this is one where the cache contains what we're looking for 90% of the time. So as long as what we're looking for is in the cache 10% of the time, having the cache turned on will cause us to break even. On average, so if what we're looking for is in the cache, 50% of the time, then it would make sense to use the cache. Okay, so just a little bit more of a concrete example. Suppose we had 2 different sizes of caches. Suppose we're considering one of 2 caches, a 32K cache and a 64K cache. So suppose the access time of the 32K cache is 1 nanosecond, because it's smaller. And what we're looking for, we notice today, because you have programs running and you don't really control what these programs do, but you notice the operating system can keep track of how many times what it's looking for is in the cache and how many times it's not. We notice 33% of the time what we're looking for is not in the cache. 66% of the time what we're looking for is in the cache. 33% is not. If you use a bigger cache, 64K, it's slower, so it takes 2 nanoseconds to read from. But what we're looking for is not there 1/6 of the time. So 5 out of 6 times it's in the cache. So because it's a bigger cache, it's more likely what we're looking for is in it. And let's say main memory takes 10 nanoseconds. And everything is in main memory. Which cache should we use? Or should we use no cache? So the expected number of time it takes to read memory with no cache would be 10 nanoseconds. If we just read straight out of main memory every time, it would take 10 nanoseconds. But if we put the 32K cache in front of the main memory, not the 64K cache, just the 32K cache, 2/3 of the time what we're looking for is in the 32K cache. So 2/3 of the time it'll take 1 second to find what we're looking for. And 1/3 of the time we're going to have to look in the cache, realize it's not there, and then look in main memory. So 1/3 of the time, it's gonna take 1 second plus 10 seconds, it's gonna take 11 seconds. So if we use the 32K cache, on average, when we go out to memory, it's gonna take 2/3 of 1 nanosecond and 1/3 of 11 nanoseconds, which is 4 1/3 nanoseconds, on average, when we go out to main memory. So that's an improvement over not using the cache. But let's consider the bigger cache. 5 out of 6 times, what we're looking for is in the cache, but this is a bigger cache, so it's slower, it takes 2 nanoseconds. And then 1 out of 6 times, we have to spend 2 nanoseconds looking in the cache. It's not there, so then we go to main memory. So 1/6 of the time it takes 12 seconds, 5/6 of the time it takes 2 seconds. We add that up, and on average it takes 3 2/3 seconds. So the 64K cache is a little better than the 32K cache. So if the operating system had both of these caches, it could keep track of these numbers and say, whatever program you're running, this is the best approach. So I'm gonna turn this cache on, and I'm gonna shut this cache off, and then hope that would work. And it could even monitor, would it make sense a little bit later to switch this cache on and switch a different cache on. So here, the 64K cache is the best option of. Obviously, if your program was very erratic and just kept hitting different data, the cache might not help at all. You might have a very high miss ratio, and then it might make sense to just get rid of the cache. Okay. Then suppose we wanted to have multiple caches. Suppose we want to have 2 caches. So again, a 32K cache, 1 nanosecond, 64K cache. So pretty much the same numbers, and then let's say in this case we're also going out to disk drive. So in this case, what we're looking for is not always in main memory. So how much time does it take to access a typical piece of storage? So if the 32K cache, suppose now we're looking in the small cache. If it's not in the small cache, we look in the big cache. If it's not in the big cache, we look in main memory. If it's not in main memory, we look on the hard drive. So let's say 50% of the time what we're looking for is in the small cache. 1/4 of the time, what we're looking for is not in the small cache, but is in the big cache. 10% of the time, it's not in either of the little caches, but it is in main memory. And then, of course, 100% of the time, it's on hard drive. So what's the expected number of time to get a piece of memory out of this system? Well, there's a 50% chance it'll be in the small cache. There's a 25% chance it won't be in the small cache, but will be in the big cache. So 25% times 3 nanoseconds. 15% of the time, what we're looking for is not in main memory 10% of the time, so that's a remainder of 15% of the time. We'll look in the small cache, it won't be there. Look in the large cache, it won't be there, and then go to main memory, we'll find it. And then 10% of the time, we're gonna look in the small cache, look in the big cache, look in main memory, and then have to go out to the disk drive. And this will give us an average time to go out to memory. So with these caches both turned on, it takes on average 14.5 nanoseconds. And now if we added that piece of hardware, the TLB, which is again a piece of hardware it's small enough that we can simultaneously check what we're looking for and find out in an instant if it's in there or not. So that means one of these wires would turn on. Out of all these comparators, one of these wires will turn on if what we're looking for is there, and none of them will turn on if it's not there, and none of them will turn on, we'll put all zeros here. So we would know instantly there were no matches. So it actually can be done, it can be checked, really independent of our cache system. So if you have the money to pay for the TLB, you might as well put it there, because what you're looking for might be there and you can find it instantly. So since the TLB can really be checked independent of our system, let's say if what we're looking for is in the TLB 20% of the time, the miss ratio is 80%, so 20% of the time what we're looking for is in there. And then we have the 32K cache, the 64K cache, main memory, and so on. So there's a 20% chance what we're looking for is in the TLB, which takes one nanosecond. 30% of the time, what we're looking for will not be in the TLB, but we'll have to spend all the time to look in the small cache. And that would be 5 nanoseconds in this case. 25% of the time it's in neither the TLB or the small cache, we have to go to the big cache. Now, the reason why it's only taking 5 nanoseconds and not 6 is because we're simultaneously checking the TLB and the small cache. We're not doing it sequentially. We're not looking in the TLB and say, oh, it's not there, now let's start the small cache. We're checking the TLB and the small cache at the same time. If the TLB finds it, a wire will turn on and we can shut off the search in the small cache. So that's why if we were following the pattern of the previous one, it would be 1 plus 5, and then 1 plus 5 plus 10. But the 1 is not there because it's being done independent. So 20% of the time we would know within 1 nanosecond. 30% of the time it's in the small cache, but not in the TLB. That takes 5 nanoseconds. 25% of the time we're going to look in the small cache, it's not there, so we'll look in the big cache. So it's small cache plus big cache time. 15% of the time it's 5 plus 10 plus 30, and 10% of the time we have to check everything. Small cache, big cache, main memory, and disk drive. And then we calculate the overall average time is 26.7 nanoseconds to check this memory hierarchy. So now the question becomes, if you're looking at a piece of memory, if I'm looking in here, and I find something here in this memory, and I want to make an update to here, is there some way, rather than going through all of this memory looking for a match, is there some way I could keep like a connection? Like if I know I'm changing something here and I want to change it here, is there some way something I could record here that tells me where it is in the previous level? So one of the techniques, this takes up space, but this is a time-saving technique, is if this is your main memory, right, here's memory location 0, 1, 2, 3, and you have some letters there. And then you have cache memory. And I have to, okay, so I have tag number 2. I have this in my cache, and I have this in my cache. So I have these 2 pieces of memory in my cache. These 2 I don't have. Now if I need to make an update, let's say I go here and I want to update this variable, I need to know where is this in my main memory and make an update there. And I might not want to take all the time to address memory. If I could do it much faster, that would help. This is where we're doing the write back method, but we don't want to spend a lot of time on it. So if I actually record not only the data and the index, so that's the address inside this memory, if I record the address inside main memory, I could write straight to that memory. So that could save time. But now it's making my cache memory, and the idea is to make the cache as small as possible. I have to make it a little bit bigger. But now I'm putting in a piece of hardware to write through quicker. Okay. Just a trick, it's an optional trick. So again, you get what the point of this is? If I'm going to make an update to my smaller cache, and I care to do a write through policy, write it back to the levels after it, it might save time if I knew exactly where to write it to. Could even put a piece of hardware that says every time I update here, it automatically updates to the corresponding next level after it, and I could run my next instruction while that's happening. Okay, and then one of the other things is, instead of making the updates at all the levels, you can make the update at the level you're at, and then independent of when your program's running, we could have our cache memories snooping, which is basically looking for changes. If the cache changed but the main memory is stale, maybe when there's a little downtime we could do our updates. So you could have 4 CPUs, each one having a level 1 cache on it. So each CPU is making updates to its own cache. And then there's a bigger main memory unit. And one of the things we're concerned about would be if CPU number 2 wants to read a variable that we made an update over here, it might get stale data. So we could have another piece of hardware, after you make an update here, another piece of hardware that's checking what you have here and what you have here to see if they're different. And if they're different, make the update, but let your program keep running. This is like a different processor making the updates for you. So just another time-saving thing we can do, rather than, so what this design is helping is, in this case, we're making X a 3. Should we take the time to write it here and write it here? So you write an instruction in Java, you say X equals 3. That line runs. Should you write the 3 here, then write it here, then write it here, then write it here, and then start your next instruction? Well, that's going to make your program run slow. What we could do is you could write it here, and then your program continues. And then a little bit later, some other process is reading saying this and this don't match. Let me write the 3 here. And then check, oh, this and this don't match. Let me write the 3 here. So they call it snooping. You're looking at the memory hierarchies and noticing if they're out of phase. Now, what if this process came a little bit later and someone else tried to read from here? This would be marked as invalid, and then it would be forced to write it all the way through before you could read it. So just different, tricks we could use to try to have the write back and write through done in such a way where you can write memory very quickly, and then it can have its value propagated later without slowing down your program.